look at the cryptography behind the IndusCrypt decipherment. By the end of this talk, you will have a clearer understanding of what a cryptogram is, how they are generally solved, and the mathematical background, and how to know whether decipherment is correct. So first of all, what is a cryptogram? Broadly, a message in a known language written in an unknown script. So there are various different variations to this, but this is kind of a broad enough definition that covers things like homophonic and other kind of related substitution ciphers. So for a long time, cryptograms were the standard in decipherments. During World War II, they invented a lot of new ways to do encryption, such as the Enigma machine by the Nazis. The United States also had, the Western, the Allies also had their own encryption schemes, including Navajo speakers to send messages and so on. So it was very complicated. But earlier, before the 20th century, cryptogram was pretty much the standard. Okay. So let us look at this small example on our screen. We have a plain text, which is EEL. It's just 3-letter plain text. And a cryptogram for this we have chosen is CCQ. So essentially E has been replaced by C and L has been replaced by Q. So what we can see is that this can be encrypted in multiple ways. So for example, we have two more examples in Latin here, HHA and KKC. And if you look at the right column, you will see that you could encrypt the same plain text using Greek alphabet, emojis, or in the final example, Indus script itself. So the Indus script example is written right to left, with the fish standing for E and the man with the jar standing for L. This particular example is from fiction, from Sherlock Holmes' Adventures of the Dancing Men. And here every drawing represents a particular English alphabet. So the first word is LC, and the word boundaries are denoted by flags. So if the character is holding a flag, it denotes the end of the word. So as you can see, the letter E is a person with outstretched raised arms and outstretched feet, but not bent. So based on whether the hands are bent, raised, legs are bent, raised, whether the person is upside down, a different letter can be encoded. And this was deciphered by Sherlock Holmes because he using frequency analysis. So he realized that the letter E is the most common and it occurs the most in this message. So he substitutes E. He guesses the first word is the name of one of the characters in the book, and then he decodes the whole message. So in this particular case, it is very simple. It is one symbol stands for one alphabet. You figure out what it is, you replace it. You can generally do this by hand. And this is the level of cryptogram that you see in newspapers that most people solve on a day-to-day basis. This particular cipher was used by Mary Queen of Scots. Mary Queen of Scots was the cousin of Queen Elizabeth I, she was imprisoned due to religious differences and the political intrigue in England. And she agreed, or she ordered, the assassination of Elizabeth I. And this message was intercepted by a cryptanalyst of Queen Elizabeth. So even in those days, they had people who created codes, who analyzed the codes, who broke the codes. And on the right side, you see a message that was sent to Mary, Queen of Scots, asking, who are your co-conspirators in code. And she would assume that this is from the proper party, and she would reply to it. Mary, Queen of Scots, ended up getting executed for treason. But if you look at the code here, it is a little more sophisticated than the previous example. You have multiple symbols for each alphabet. So the letter A has 4 symbols and so on. And on the right, you see the letters that you see digraphs like E, A, O, O. They have their own symbols. And in the center, you see the months of the year and the words like madam and all these, the words that start a letter have their own symbols. This is to defeat frequency analysis that Sherlock Holmes used in the previous example. There are also nulls. You can see below the letters in the center there are nulls. Nulls are just spaces. They have no value. They are just put in between the message to confound the cryptanalysis. So recently, there was a codex, which is the name for a book written, in an ancient language, that was written in the 1730s, which was cracked in 2011 using computers. This is called the Cryptogram Cipher, and it's what's called a homophonic cipher. So what happens here is the number of substitutions is not the number of possible substitutions is proportional to the frequency of the letter in the language. So in English, for example, E occurs about 12% of the time. So you would have 12 times more symbols for E than some other letter that occurs only 1% of the time. So that gives you a kind of uniform spread of symbols and defeats most of the cryptanalysis based on frequency. But this was cracked using computers. They guessed the language was German because somewhere in the margins of the book, the name Philipp was written in a German spelling, in a German variation of the spelling. So they guessed it was German, and they used computer programs to try different permutations, and they found that this was German, and they decoded this text. This is a letter from the Zodiac killer, and this was in 1969. The Zodiac killer sent letters to newspapers and also to the police, and some of them were encrypted as a cryptogram. This was cracked by 2 people, both last name Harden, and this is their worksheet. And they were able to, so once they cracked it, the next cipher, called the 340 cipher, was more complex. You can read that. There are videos on how it was created and crafted. But what you see here, for example, in the leftmost section, the message starts with I like. So the first letter and the third letter, represented by delta and P, they both represent the letter I. So it is kind of normal in a cryptogram, in a slightly more difficult cryptogram, to have more than one symbol represent the same letter. So how do you solve cryptograms? Let us quickly go through some examples. The cryptograms are essentially solved using, there are various algorithms, right? So one is called statistics. Statistics is again how many the frequency analysis, what letter stands next to the and what is the likelihood of this particular sequence of letters occurring in a language, and so on. Dictionary is a more is a different way of doing of solving. Essentially, it's based on the fact that certain words have certain patterns in a certain language, and this is what essentially we do when we decipher the index script. So let us start with the word cat. It's a very simple three-letter word, and we'll use the dictionary method to solve it. And you can see there are many solutions. I think there are 500 something solutions, and the reason is any three-letter word that doesn't have a repeating letter is a valid solution. So it has a lot of ambiguity, a lot of equivocation. So now let's try other messages, things that are slightly longer. So we are going to try cat, dog, bird and see what we get. And you see that it's still, there's a lot of ambiguity. It could be anything. It could be, it all sounds nonsensical because although you have a solution, it may not make sense. Let's try something longer. This is bigger words. So far we've been trying short words, so let's see what happens if we use bigger words. So now it's very, very close. The first word does not have any alternatives. The second word, if you look at it, all the alternatives are in very few letters. The letter N seems to be fixed and the letter L seems to be fixed, but there is some play with the other two letters. So this is what happens when you have words with repeating letters that are at the same letters at the beginning and the end. Here, for example, in millennium, you have a double L, you have a double N, and you have the first and last letters the same, and you have I that repeats in different positions. So this pattern doesn't exist in many words. So in fact, it exists in only one word in English, which is why that is the only result for that word. So now let's try a longer sentence with shorter words. This is a famous children's rhyme. And as you can see, the word little and LAM is fixed. There's not a lot of play in those two words. The last word is either a lamb or a lamp, because the L and the M are already fixed in the choice of your first word. And the first word, your MA is fixed, and there's a little play there, but not a lot. So it is as we take bigger and bigger sentences, the amount of equivocation reduces. There's not a lot of play. So in this, it's a big word. It's only one word. It's a big word, but the pattern here, it results in only one solution. And also, you don't have a lot of words with that length in the dictionary. So let's try many short words, see what happens. So there's not a lot of play here. The free Cree, the Cree is a name of a tribe. It's not a real word. Neither is Bree. So at this point, you're coming to a place where you can only solve it in one way, right? The cryptograms are coming to a place where you can only solve it in one way. So let's try something longer again. So here, this is 5 words, but these are medium to long words. And there really is only one choice. It's essentially, you have reached a point where you cannot solve it in more than one way, right? We can try something longer. This is, let's choose the Gettysburg Address. This is from Abraham Lincoln's speech in Gettysburg. And, it can only be solved in one way, because there's only so many combinations that are possible, where you need to have a letter of a 3-letter word that is the same as the letter for a 6-letter word, and so on. So that you are going to run out of patterns that will fit the message. Okay, so now we could scramble this message, and so it doesn't matter, because those are dummy variables. But I could scramble it a few times, it wouldn't matter, because those are all dummy variables to the solution. So if you solve it, it's going to return the same thing. Okay, because the solution only looks at patterns, and all it cares is this letter repeats here, and you could replace it with numbers or anything. It doesn't matter. The solution, the mechanism of the solution is the same. So now let's see what happens if you let's try to solve something in a different language. So this is a different website, which it's not as convenient as the other one, but this has it has an advantage of solving in different languages. So here, for example, here I have these 2 choices. If I choose fluorescent, that's it. This has, it's very close. I don't even know if this is a proper word, but it solves it in this one way. So let's try solving it as German. German is close enough to English that maybe there's a match. So let's do German. And so what you see here is that there is no pattern that matches this particular word. There's nothing in the dictionary. 0. So you cannot solve that message as German regardless of what you do, because this particular pattern simply doesn't exist in all the words in that dictionary. So but what maybe they are in a different dictionary. We can try some other language, maybe Dutch. So let's see what languages actually have those patterns. So we can use regular expressions. So essentially the dictionary method can be modeled as regular expressions. So I'm just going to try to see what other languages have this pattern. Okay, so the word is cookbooks, didn't fit. So you have a dot that repeats, and you have another word, and the whole thing repeats, and there's another letter. If you don't understand regular expressions, just bear with me. All right, so you have it in these three languages. You have Dutch and Spanish. So let's also print the actual words in Dutch. So there is a certain word. See, oh no, wait a second. This is not the one. Yeah, this is it. So you have English, American English, you have Dutch, and Polish on Portuguese. So all of these should be good. Dutch has a lot of matches, so we'll go with Dutch. And let's see if we can read this as Dutch. Right, so what it's doing now is downloading the Dutch dictionary and is going through it every time. The first time you try a new language, it takes a little bit of time. So it doesn't work. It cannot solve it as Dutch. So even though you had just this, it matched for this, it couldn't figure out how to solve this. So this is one of the issues. You cannot really solve a message in a different language. Now you can do it for something short. So I'm sure for, say, Mary had a little lamb, it should be possible to get some messages. So let's try it in Dutch. And see, I have these options. So for the word little, I'm going to choose say, okay. And I mean, I couldn't do it, I couldn't choose the right ones, but it is possible that if I choose the proper words, I could get something in Dutch. We could try something shorter just to have a proof of concept that short messages can be read as a different language. So for example, here we have a lot of choices because these are tiny words, and it so many of these are spurious words. They don't actually mean anything. So so I don't know actually if dat, ik, abri means anything in Dutch, but you theoretically could solve a short cryptogram as a different language, but for a long cryptogram beyond a certain size, it is simply not possible. Okay, so if you extending the same logic to the index script, what we see is that when you see these examples, you have three symbols in an inscription. These are two different inscriptions, and most languages will fail to match here, because if you see the same regular expression here, I'm trying to get anything, any letter, and match two other occurrences of the same letter, and then have anything at the end of it. So that should match this one and this one, but you get no results. So let us, so it wouldn't work in English, for example. So let's forget this. Let's say we will decode this later. Let's go on a different branch, find a different seals, and try to solve them. So we'll go with this, and as you have seen, this, if I do, if I go with American English, and if I go with, so what this is saying is, I want to capture one letter. The second letter has to be the same as the next letter, and the third letter can be anything. So I'm looking for some letter as the first one, the second one as the exact same letter, and the last one as any letter. I want to see what I can match in English. And I get EAL. DDT is an acronym, it's not a word. So I get EAL, which means in English, if I were to read the Indus script as English, the fish would be E, and the man carrying jars would be L. Okay, so if we have these values, we can try to solve the next one, which is any two-letter word that ends in L. Now let's see if something like that exists. So I would be saying the first letter could be anything, the second letter has to be L. There's no such word. So what has happened is I have hit another dead end. So I could try with more word, different seals, different inscriptions, and try to keep solving, but eventually it will all take me to a dead end if I try to decode it or decipher it in a language that is not the actual language of the inscriptions. Okay, so we'll try to see why that is. So a lot of the analysis on cryptograms, deep analysis, was done by Claude Shannon in 1945. So 1945 was World War II. There was a lot of involvement of cryptography, cryptanalysis in the war effort. And his paper was so groundbreaking that it was classified by the government. So I have the paper here. You can read it at leisure, but this is a very famous paper. It was classified, and over time parts of it were declassified. So the portions of this paper that are not to do with cryptography was released as another paper in 1948. So this is the mathematical theory of communication. The 1945 paper is the mathematical theory of cryptography. So everything you do today on your computers, encryption, signaling, sending signals across wires, data compression, all of this come from this paper. This is the foundation of all information theory. It wouldn't be an exaggeration to say without this paper we wouldn't have computers and computer science, information theory, and those things that we take for granted today. Okay, but in the 45 paper, this really is about encryption, and there is deep study on cryptograms, how to model a cryptogram, how to solve it, and how to know that you have solved the cryptogram accurately. So you can go through this paper. If you are a computer science, if you're an engineering background, if you haven't read the 45 and 48 papers, I suggest you read them. It is really a seminal paper that everyone should be familiar with. If you're not engineering, you won't be interested in it. Okay. So this was the paper, and the cryptography is in the 1945 paper. And what is in that paper? So the language is modeled as a Markov process, and a Markov process essentially is that there is a state or more than one state. In this example, this is a very simple language. There's only one state, the dot in the center. And this state generates a symbol with a particular probability. So in this example, it generates the letter A with 0.4 or 40% of the time, and it generates B 10% of the time, and so on. All of them add to 100%, and the language it generates would look like this. So this is a very simple language you can use for analysis and so on. It's easy to code. Real languages are more complex. This is a slightly more complicated language with words, and you can also model it as idioms and phrases and so on, where you have a lot more states and you have a lot more transitions with different probabilities. So here, for example, BADD is only 1%, but BEBE is 16% of the time. And these patterns that are generated, the letters, the patterns of here there are letters, but it could be phonemes, it could be graphemes, it could be phrases, it could be idioms. All of these are patterns that are generated by this Markov process. They are unique to a language. So you can see these three, they will never generate the same things. The probability of them generating anything same is very, very low, and it's for very, very short words, which is why you saw when we tried to solve that cryptogram in that website, for short words and for short phrases, you had a chance of being able to solve it in a different language. But anything with large words, anything where the message is a bit larger, it would simply not match. Okay, and this is the reason, because it's the nature of language itself to create patterns that are unique to that language, which are simply random, it is random garbage in a different language. Which is also why when you are in a restaurant, someone next to you is speaking a different language that you are not familiar with, you don't understand anything. And it's only when they say a word that is a borrowed word, let's say they say mobile or email or telephone, you only understand that word and the rest of it just bypasses you. It is because of the structure of human language itself. But can you force read a language as another language? And here is an attempt to do that. At the bottom you have this famous poem from the 700s Japan, and what we have done here is we have rendered it in hiragana. Japanese has three different symbol systems. Hiragana is one of them. So for simplicity, we have rendered the whole poem in hiragana, and we have mapped hiragana letters to English alphabets. And when we transliterate the poem in English letters, you see what is in the middle. It is simply unreadable. And the reason is, when you do that, that actually is what a cryptogram is. You're writing something in one language in the alphabet of another, in a totally different symbol set. That's a cryptogram. It's not a solution. So you won't be able to simply force reading in a language of your choice by just assigning values to symbols. Now that was random assignment, but can you do a little better using the knowledge of frequencies? Let's say you add more E's and THs and all that. So that is called approximations, first order, second order approximation. So when there is zero approximation, it's just random. First order approximation, you use your knowledge of symbols, frequencies of symbols. Second order, you do your knowledge of two symbols, the frequency of their occurrence together, and so on. And what happens is, it kind of sounds English, but it's still nonsensical. The reason it sounds English is because you have now entire syllables that are actually from English, because you use those frequencies to assign it. Okay, but it's still not possible. Now, can you theoretically figure out an optimal solution to that problem? Find a certain set of words that you want to fit and try to assign it using any kind of computation. And here we have done it manually, and of course we've cheated because we put O and S as the same. On the right in the blue, we put O and S as the same symbol because we had to handcraft this thing. And in theory, the red graph representing Sanskrit words is a subgraph of the right, which is English. And in theory, for this little bit of alphabet, little bit of symbols, I could read it as English, right? But in a general language, in any large corpus, English has 300,000 or more words, and Sanskrit has God knows how many words. But if you try to do that, that problem is called subgraph isomorphism problem, and that is an NP-complete problem. It is not, at present, it's not solvable. So you cannot really do it at all. So what does Shannon have to say about correct decipherment? When is a decipherment correct? So if you look at this decipherment as a black box is one where you cannot see how it works. You cannot see what's inside it, and you have a ciphertext, right? Ciphertext is the encoded text. You push it in the black box, and out comes a plain text. How do you know this decipherment is working correctly? So in our case here, the ciphertext is one letter, it's A, and the output is a whole line, and it could even print out the entire Harry Potter series or the complete works of Shakespeare based on your 1 or 2 or 3 letters that you on a different letter you put in the input. Now, what does this mean? What does this tell you? Does that letter A have all the information that's generated outside? Is it possible to encode an entire the entire full works of Shakespeare into one letter? It's not, right? What this means is that the information that's output actually resides in the black box, and it's only using the input as a switch to select what comes out. Okay, so this is the black box, and you just figured out that the source of information is the black box, A is the switch. Now let's look at a white box. A white box essentially is something you can examine. You may not understand how it works, but you are able to ascertain that it doesn't have any kind of storage. Okay, so in this example, you take the input A, and it uses a large key as an input, and it generates the same output. Mary Had a Little Lamb or the full works of Shakespeare. So logically here, since the input A doesn't have enough information to match the output, it must have come from the key, because the key is very large, and the white box doesn't have any kind of storage, so it must have come from the key. Okay, so let's look at another example here where the plain text, the ciphertext is very, very large and the key is very, very small. So here, when you get the output, you can be reasonably sure that the source of information comes from the plain text. It comes from the input on the left and not from the key, because the key is too small to generate that kind of output, that size of output. So it must be from the input. So this, you are going to say, is a reliable decipherment. On the other hand, if you have a large input and an extremely large key, and then you have an output, you don't know where the key is coming from. So it is kind of a suspect decipherment. It could be from the key. The decipherment could be from the key itself. Now, all of this seems to be common sense, right? What is special about this? if information is of a certain size is being generated, it probably comes from the path which has enough information of that size or more. So this is essentially it. You are saying that it's valid if the key is much smaller than the plain text. This is just common sense. Now what Shannon did was he figured out a numeric limit for it. He calculated at what point you can be certain that the decipherment is correct. And his formula is given here. Essentially, what it says is the size of the key, which is essentially log of the number of symbols, factorial of the number of symbols, and the redundancy. You divide one by the other, and that tells you how much it is. So in English, for example, you have 26 symbols. So the number of keys you have is the number of ways you can arrange 26 symbols, which is 26 factorial. So the first symbol can be picked 26 ways, the second can be picked 25 ways, and so on. And so you just multiply them, you get the size of the key, and you have to take log 10, and then you divide it by redundancy. Redundancy is how many symbols are filler that you don't actually need to get the information. So in other words, in English, using 30% of the letters, you can guess the other 70%. So 70% is redundant. So unicity distance is simply log of 26 factorial by 0.7, which is about 30 letters. Okay. So if the deciphered text is much larger than 30 letters, then you can consider that as reliable. So which is what you may have seen when we did all the decipherments. When it crosses about 30 letters, it starts becoming unique. So the unicity metric is just far away, so 1.5 times that distance. So for Sanskrit and Indus script, we have 417 symbols and you have 35 phonemes. You get about 1022, and if you reuse the aspirates and retroflex and sibilants, you get 1107. So roughly around 1100 or 1200 symbols. If you solve it, then you are well into reliable decipherment. So what we have done is we have deciphered almost all the signs, deciphered the 50 longest inscriptions, which no one else has deciphered meaningfully so far, and we've deciphered well over 1100 signs. We have deciphered about 3 to 4 times that limit, which is way beyond. So yes, so this is the only decipherment which has deciphered every symbol, every inscription, the only one that's cryptographically sound, and it uses a proven method, something that anyone can read and write, not just the decipherer, and it's in an attested language. What that means is a lot of decipherments are in a language that the decipherer not made up, but they kind of had to determine that it has to be this kind of unknown stage of a language. Okay, so in an attested language, it's always more credible, right? So when I say the Pearl monks here, let me show what the whole regular expression stuff to solve cryptograms is it's here. It's documented as 2007, but people were doing it even as far back as 1997. And essentially, this is what you saw me doing. You can do that, and it will find all the words that match that symbol, that pattern. Okay. So that's essentially the presentation. I hope you find this useful. Please like, comment, share, and tell me what you think. I hope this has been useful.